Welcome to the deep dive. We're carrying on with our series looking into the OEIS, the Online Encyclopedia of Integer Sequences. And this time we're hitting a topic that, well, it really connects geometry and number theory in I think, a pretty beautiful way.
Yes, exactly. We're looking at OEIS sequence A00023, and it comes from what seems like a simple enough question, geometrically speaking.
Okay.
Imagine a sphere in 3 dimensions. How many points, integer coordinate points, lattice points, lie inside it or right on a surface?
Right. Okay, I can picture that. A sphere centered at 0, 0, 0, and as it gets bigger, it captures more of these grid points.
Precisely. And if we use n to represent the radius squared of this sphere,
Oh, radius squared. Okay.
then there's this count, let's call it A-nan for now, which is the number of integer triples, I, j, k, such that I squared plus j squared plus k squared is less than or equal to n. A00023 is related to this an.
Got it. I plus j plus co n. That's the condition.
Now, on the other hand, you could just calculate the sphere's volume. Forget the integer points for a second, just the smooth, continuous volume.
Standard formula, right.
Yeah, Vn equals 43 times the radius cubed. Since n is radius squared, the radius is n, so the volume is 43 times n to the power of 32.
Okay, so an is the discrete count, vnn is the continuous volume. And the interesting part is how they relate, or maybe how they don't quite match up.
That's exactly it. We define this difference, Pn is an minus Vn.
The count minus the volume.
Right. Think of it as the error or the discrepancy you get if you try to approximate the number of lattice points just by using the sphere's volume.
And this sequence, A0000023, tells us something about this error, Pn.
It tells us about the extremes of this error. There's another sequence, A0000092, that lists the n values, where the absolute value of Pn, so an Vn, hits a new record high.
Ah, okay, so A0000092 finds the n where the error is biggest so far.
And A00223, the sequence for today, gives us the value of Pn, well, probably the nearest integer to Pn for those record-setting in values found in A0000002.
I see. The first few terms are 3, 7, 10, 19. So these are the sizes of those record errors, more or less.
Exactly. And our mission, if you like, for this deep dive is to unpack this relationship, the discrete points versus the continuous volume for a sphere, and why this difference, this Pn, is actually quite significant in number theory.
This whole idea, comparing a point count to a continuous area or volume, it sounds a bit familiar. Isn't there something called the Gauss circle problem?
Yes, absolutely. That's the classic two-dimensional analog.
Oh, that's right.
Sources like Wikipedia, and I think it came up in that Reddit thread too, mention it.
So instead of a sphere, it's a circle in 2D.
Right. You count the integer points, IHA, such that I-nan plus jo is less than or equal to the radius squared, let's say r. Call that count nr.
And you compare it to the circle's area, r.
Exactly. nr is approximately mar.
What?
Again, it's not perfect. There's an error term, er, so nr plus er.
And finding out how big that er gets is, well, it's a whole thing in itself, isn't it? I remember seeing something about the exponents.
It is a major problem. We know the error, er, grows slower than the area. It's bounded by something like c times r to the power of t. Finding the true value of this exponent t is famously difficult.
Wikipedia mentions it's somewhere between 12 and 131208, something like that.
That's right, approximately 0.63. So definitely less than 1, meaning the relative error shrinks, but pinning down the exact rate is hard.
So even in 2D, the grid points don't perfectly fill the shape, volume-wise.
Precisely. And our 3D sphere problem with an and vn is just the next step up. Same fundamental question. How well does the smooth volume approximate the jagged count of integer points?
Which means our Pn, the ANVN, is basically the 3D version of that error term, ER.
That's a perfect way to think about it. Pn is the error term for the sphere.
And the OEIS page for A000C23 actually shows some Mathematica code for calculating it.
It does, yeah. It gives a practical way to compute Pns. It sums up a function called squares R3, k for k, going from 0 up to n.
Squares R3, k, what's that?
That function counts the number of ways you can write the integer k as a sum of 3 squares, including order and signs of the roots.
Ah, so it's directly counting the lattice points on shells of radius.
Essentially, yes.
Right.
You sum those counts up for all shells up to radius gen, which gives you the total count an. Then the code subtracts the rounded volume vn, and voila, you have Pn.
So you can actually compute the error directly if you can compute those sums of squares representations.
Right. But of course, number theorists want more than just computation for specific n. They want to understand the asymptotic behavior. How does this error Pn grow as n gets really, really large?
And that's where the bounds come in, like for the circle problem.
Exactly. People often use Rx for the remainder term where x is Rn, so Ax 43, x 32, plus Rx. The goal is to find how fast Rx grows.
Okay, so what do we know about Rx?
Well, one of the foundational results mentioned in the lattice points in a sphere paper is from Walfus. He showed that Rx is Ox12.
Big O notation, meaning it grows no faster than some constant times the square root of x as x goes to infinity.
Correct. It gives an upper limit on the growth rate.
Has that been improved? Like the circle problem bounds were refined?
Yes, significantly. Vinogradov later showed Rx is Ox34 log x. That logarithmic factor is minor compared to the change in the exponent from 12. Oh, wait, my apologies. Walfus's result was actually better. It was Ox23. Vinogradov improved that to something slightly better involving logarithms, but the best known bound is actually Ox2132 plus a by Heath Brown. There were earlier, perhaps easier to prove, but weaker bounds mentioned too, like Ox43 or even Ox1 plus a, which are much simpler estimates.
Okay, so the goal is always to push that exponent down to show the error grows as slowly as possible relative to the main volume term.
That's the game. A smaller exponent means the lattice points are, in a sense, more uniformly distributed, and the volume is a better approximation sooner.
And RPN is just this Rn. It is the remainder term we're trying to bound.
Precisely. A00223 tracks the extreme values of this very remainder term.
It's fascinating how it connects. Now, you mentioned higher dimensions. The Reddit discussion touched on generalizing this.
It did, yeah. Someone proposed a recursive way to think about it.
Yeah.
Let SDR be the count in d dimensions for radius r.
Okay.
They suggested you could get the count in n plus 1 dimensions, s to n plus 1 r, by taking the count in n dimensions, s n r, and adding contributions from layers, specifically adding twice the sum for k from 1 to floor of SDR's k.
That looks like you're slicing the n plus 1 dimensional sphere and summing up counts in the n dimensional slices.
That's the idea behind it. It gives a way to relate dimensions, but computationally.
It looks like it would get really messy really fast.
Absolutely. Finding closed forms or even good error bounds gets exponentially harder as the dimension d increases. The geometry gets much more complex.
Yeah, I can imagine. It seems like we need different tools for these harder problems. You mentioned another paper, lattice point counting and harmonic analysis. That sounds like a different angle.
It is. Harmonic analysis, think Fourier analysis, and related techniques provides a powerful lens. They frame the general problem as counting points NR in a scaled region RB.
R is the scaling factor, B is the basic shape, like our sphere.
Right. And the error is, again, ER, NR, vol B, where D is the dimension.
Okay.
Harmonic analysis tries to find the error exponent, often called theta D, theta by E 20 by 8, 20 by 90, which is the smallest alpha such that ER is O. It characterizes the true growth rate of the error.
So what does this approach tell us about our 3D sphere case, about D?
Well, the paper mentions that even a fairly basic harmonic analysis approach using smoothing functions can show that EORs is less than or equal to 1. This corresponds to Rx being Ox1 plus E, which is weaker than the best known bounds but derived through these analytic methods. Getting the better bounds often involves, well, it gets complicated.
The paper mentioned exponential sums.
Yes, that's key. The error term isn't smooth. It oscillates. These oscillations are captured by exponential sums that arise from the Fourier analysis of the lattice points.
Like summing up complex exponentials.
Exactly. Getting good bounds on the error term relies heavily on showing that there's significant cancellation in these sums, proving that cancellation is often the hardest part.
Wow. And the paper also throws in a connection to L functions. That sounds like deep number theory.
It is. This is where things get really advanced. Dirichlet L functions are crucial tools in analytic number theory, especially related to prime numbers.
Like the Riemann hypothesis connection?
Well, the Riemann hypothesis is about the Riemann zeta function. But Dirichlet L functions are generalizations. It turns out that the properties of certain L functions, specifically where their zeros lie, seem to be intrinsically linked to the error term in the sphere problem and potentially other lattice point problems too.
So improvements in understanding L functions could lead to better bounds on our X.
That's the hope and belief in the field, yes. It shows how interconnected everything is: geometry, analysis, and the deepest parts of number theory concerning primes and zeta functions.
It really does weave together. And just to loop back to the OEIS itself, the page for A0000003 links to other sequences like A00000000099, Are these just related problems?
Often, yes. Those links might point to sequences counting sums of squares in different dimensions, or perhaps related arithmetic functions, or maybe sequences arising from similar analytic number theory contexts. Exploring those connections can give you a broader picture. See how this one problem fits into the larger web of number theory.
Right. So let's try to summarize what we've covered about A00023.
Sounds good.
We started with the basic idea, counting integer points in a 3D sphere, AN,
Compared it to the sphere's volume, Vn, NOA 43, AIM 32.
and focused on the difference PN, AN, VN, the error term.
We saw that A0000223 tracks the record-breaking values of this error Pn.
We drew an analogy with the simpler 2D Gauss circle problem and its error term ER.
Then we looked at the bounds established for the 3D error term Rx, or Pn, like Walthus's and subsequent improvements, trying to pin down its growth rate.
We touched on generalizing to higher dimensions and the complexity that brings.
And we saw how powerful techniques like harmonic analysis come into play, framing the problem in terms of error exponents and highlighting the role of tricky exponential sums.
And finally, the connection, however deep, to Dirichlet L functions, suggesting the problem is tied into some fundamental aspects of number theory.
That covers the main threads, I think.
It's really something, isn't it? How a question that sounds almost like a simple geometry puzzle, just count the points, leads you down these paths into really advanced analysis and number theory.
It truly is. It shows that even with basic shapes like spheres, understanding the fine details of how discrete objects like integers interact with continuous space is incredibly rich and still holds many challenges for mathematicians. There are still open questions here.
Definitely makes you appreciate the sort of tension between the smooth world of geometry and the lumpy world of integers. And number theory is the toolkit we use to measure that tension.
An excellent way to put it.
Well, we hope this gives you a good starting point to explore A0000223 and the fascinating area of lattice point problems further. Thanks for joining us on this deep dive.